Welcome to my licentiate seminar. Today I would like to present my work, X-ray fluorescence spectrometries for environmental applications. This thesis work includes 5 parts: the introduction, X-ray fluorescence serial, methodology, results and discussions, and the conclusions. As human beings, we produce trash every day, and it could be the newspapers, the plastics, metals, and with the world population, we generate 2.01 billion tons per year. Incineration is one of the waste treatment methods that involves the combustion of organic substance in the waste materials. There are several advantages of the incineration process. During the burning process, it decreases the volume and the weight of the waste, and at the same time, it produces the heat and electricity. In some countries, the incineration plant is integrated with the city heating systems. Since the incineration plant can be built close to the city, so it saves the transportation time to transport the waste to the landfilling field. And comparing to the landfilling methods, the incineration prevents the production of methane gas. In the end, the burnt gas can be used in some construction works. So because of these advantages of the incinerations, the incineration has been widely adopted by around the world. And these two figures show the treatment of collected municipal solid waste in Sweden and in Finland. Both figures show that there is an increasement of material recycling and energy recovery from the waste. It results in a decrease in landfilling. However, heavy metals in the waste were accumulated into the fly ash and reach a high concentration level in the end. So fly ash is regarded as hazard waste and has to be pre-treated before landfillings. Sundsvall incineration plant implements a washing process that allows storage of fly ash on landfilling for non-hazard waste. The washing process generates a mixture of fly ash and sludge that has low leaching of metal content to the surroundings. However, there is a risk that the dissolution content from the solid phase can leach it out into the solids phase through the rainwater. So it is necessary to regularly monitoring the elemental compositions in both fly ash and the leachate. Since toxic elements pose risk to the ecosystem and human health, this table below shows the standard limitation of hazard elements in fly ash from 3 different areas in the world. So far, the Sundsvall incineration plant collected the fly ash sample and mixed the sample to get an average concentrations. This offline laboratory element analysis has some disadvantages, such as there is a significant time delay between the collection of sample and the analytical process. There is a lack of immediate feedback and make it difficult to adapt the washing process on site. For liquid samples, the existing measurement methodologies also involve complicated sample preparation techniques. So a suitable technique should have the following characteristics. It should be able to perform in situ measurement, which means that we don't need to collect the sample physically. Instead, the instrumentation can be placed in situ, and the system should have a reasonable accuracy so that we could detect the heavy metals, which is below the allowed limitations according to the law. In the end, the perceived data should be analyzed online so that it is possible to improve the washing process and give immediate feedback. This project is a feasibility study of online X-ray fluorescence instrumentation for continuous and direct analysis of environmental applications and industrial process. There are 4 specific research questions are addressed. What is the performance of the qualitative and semi-quantitative analysis of XRS method and SIM-EDS method? Those 2 methods are similar since both of them are based on the emission of characteristic lines. And the second question is how to optimize the signal-to-noise ratio in the XRF spectrum for a direct analysis. In the third one, we investigate 2 types of X-ray optics. One is using a pinhole optic, one is polycapillary optics in a full-field XRF imaging system. In the end, we investigate the scanning XRF method to obtain, if it's possible, to obtain a light element distribution in a few millimeter size. X-rays were discovered in 1985, and it can be seen as electromagnetic waves with their associated energies. Depending on the interactions of X-rays and matter, there are several different applications use different parts of X-ray spectrum. For example, the X-ray crystallography can be used to determine the atomic structure of a crystal. And there are also medical applications for high energies, the airport security, also based on the X-ray technologies. Above all these applications, the X-ray can also be used to identify the elements based on the interaction between the X-rays and the atom. There are 2 main interactions involved in this thesis. The first one is called photoelectric effect. At energies of few electronvolts to few kiloelectronvolts, a photon can be completely absorbed by, and its energy can inject an electron from the host atom. This process is known as photoelectric effect. So in order to inject an electron from the atom, the incident photon energy should be bigger than the binding energy of the electrons. In the second is called Compton Scattering, which is the most important interactions in the mid-energy range. It is the scattering of a photon by a charged particle. In this case, it is electrons. Compton effect results in a decrease in energy of the photon, and since part of the energy is transferred to the recoil electrons. However, there are more interactions might happen, like coherent scatter, which is similar with Compton scattering, but instead there is no energy loss in this case. And for high energy incident photons, it could interact with the nucleus and result in a pair of electron and a positron. But these 2 interactions were not included in this thesis work. So once an electron is injected from the atom, then the atom is in an unstable status. So the electron in the outer shell will fall into the inner shell to fill the hole. And since the electron in the outer shell has higher energy than the inner shell electrons, in this falling process, the energy is released in the form of a photon. The energy of the characteristic radiation equals to the energy difference of the two shells involved. For example, in this table, the emission line, the characteristic X-ray emission line from chromium, the K alpha lines means that an electron in the K shell is ejected while an electron in the L shell fill the holes in the K shell, and this line called K alpha. XRF sample preparation is a precise methodology for preparing analytes for elemental composition analytes. Usually, the analytes for loose powder is required. The sample is placed into a plastic cup or pressed into pellets. The pellet sample preparation is essential for accurate analysis. However, for the purpose for online measurement, a minimal sample preparation was expected. Since XRF is a bulk analysis technique, so we just roughly ground the fly ash sample and make sure that to ensure a reasonable flight surface. For the unwashed sample is fine powder, so no specific sample preparation was carried out. For liquid samples, there are three common ways to prepare the sample. One is using a liquid cell. The sample is placed in a container and be analyzed. This enables a direct analysis. The second one is to use a filter paper. Then the paper is dried in an oven. The third is concentration process, such as solid phase extraction process, where we extract the element of interest from the liquid sample. And on the right figure, it shows the chromium calibration samples, which is made by a chromium compound. And the yellow bottle shows in the figure is the leachate sample that we collected from the incineration. In the analysis of toxic substance in the environment, the most important characteristic of analytical procedure is the limit of detection. For a commercial X-ray spectrometer, the detection limit ranges from 100 down to few ppm levels, while for the liquid samples, it usually suffers a high scattering background noise. So signal-to-noise ratio is one of the denoising evaluation index. The definition of SNR is the total count, which includes both the signal and the background, minus the background noise, and then divided by the noise, which is the square root of the background signal. And a well-common accepted definition for limit of detection is when the SNR is greater than 3, which means that the characteristic peak of an element at a concentration is greater than a background by a statistically significant amount. This figure shows a typical energy dispersive XRF setup. It includes two parts: the X-ray tube, which is irradiates the sample, and a detector which recorded the fluorescence emission lines from the sample. As shown in Figure 1, the primary X-ray beam contains two parts of X-rays, the continuous X-rays and the characteristic radiation, which is coming from the target material in the X-ray tube. So by placing an X-ray filter between the X-ray tube and the sample, it acts as an X-ray absorber, and it removes the photons with low energies, and also it rectifies the output spectrum as shown in Figure 2. In this filtered spectrum, we could see a much lower background noise at 5.4 kilo-electrovolts, where is the chromium K alpha lens. And then in Figure 3 shows the spectrum of chromium liquid samples with a series of copper filter ranging with a thickness ranging from 20 micrometers to 160 micrometers. The chromium peak at 5.4 kilo-electrovolts is clearly resolved with the filter thickness increasing. To study how the X-ray filter affects the SNR, two filter materials, copper and germanium, with varying thickness are compared. We calculate the SNR for the chromium peak from the experiment and the simulations. And for both materials, the SNR increases with the filter thickness increasing and reach a saturation value. However, the intensity of the X-ray beam is exponentially decreased with the filter thickness increasing. So there is a trade-off between a high SNR and a short measurement time. For a practical XRF setup, we suggest a copper filter with a thickness from 100 micrometers to 150 micrometers for the optimization for chromium. For inhomogeneous samples, the XRF imaging, which contains the elemental distribution information, can be obtained by two methods. The first one is called the scanning method, where the sample surface in 2 dimensions is scanned with a micro-focused X-ray beam. The second one is called the projection method. In this case, the full field of the elemental distribution is projected on a 2-dimensional pixel detector. As shown below, a photo of a rock sample from Arno from the local Sundsvall is shown in below. It contains two areas, the dark area and the white area. Since the iron element only exists in the dark area, so we extract the iron peaks and then plot it in the XRF image. In this image, the brighter area shows there are more irons, which shows agreement with the sample. Due to the isotropic emission of X-ray fluorescence from the sample, an additional X-ray optics between the sample and the pixel detector is required to collimate the photons. These two figures shows the Pinhole Collimator and the polycapillary collimators. Since the physical phenomena are different, for the pinhole camera, it generates a mirrored image, while the polycapillary optics use totally external reflection to get the X-rays through tiny glasses tubes, and it generates a non-reversing image. In a straight polycapillary optics, there are 4 interactions might happen. When the photons has high energy, it could transmit the inner walls of the polycapillary, or it could generate the fluorescence signal from the capillary materials. If the incident angle is below the critical angle, total reflection will happen. And the critical angle is given by the material density and the incident energy of the photon. And in the end, there is a small amount of photons might pass through the inner walls without any interaction. In a polycapillary optics, the ideal collimated X-rays are the photons, which are totally reflected on the capillary walls without an energy loss. So we compared the qualitative and semi-quantitative analysis of XRF method and same EDS method. These two methods are two similar methods, and in the XRF measurement, X-ray tube was used, while in the same EDS, electron gun was used to generate the fluorescence of the sample. Since in this, we compared the washed sample and the unwashed sample. So both methods could able to determine the elemental composition in the fly ash samples, while the semi-quantitative analysis allows us to compare the spectral data from these washed and unwashed samples to obtain the information about the relative concentrations. But in the same EDS measurement, it performed in the vacuum chamber, while in the XRF measurement is performed in the air. So the same EDS gives a much better resolution for the light elements. We used a 100 micrometer copper filter and a 300 microgermanium filter to optimize the chromium measurement in liquid samples. The germanium filter with 300 micrometer is not the optimal choice when concerning the exposure time, but that it was a valuable filter, and it gives a saturated XNR. 5 calibration samples from a 3.9 milligram per liter to 0.25 milligram per liter was measured. These samples are compared with the purified water and the leachate sample. Since the peak area is related to the concentrations, the highest concentration gives the highest peak in this case. By reading from the figures, we see 0.25 milligram per liter and 0.5 milligram per liter is the detection limit of copper filter and the germanium filter. Below these concentrations, we could not distinguish the chromium peak from the background. These figures show the relationship between the chromium concentration and the SNR. Since the definition of the limit of detection is when the SNR is larger than 3, a right dashed line is marked at SNR equals 3. And we read that in this simulation, the detection limit for copper filter is 0.25. For germanium is 0.3 milligram per liter. It shows agreement with the experiment. In order to study the spatial resolution of X-ray collimation systems, we compared the two setups based on the pinhole camera and the polycapillary setups. First, the figure A and B, which has the same sample to optic distance, are compared. Then figure A is compared to figure 3, where these two setups achieve a similar spatial resolution. So the picture below shows that the resolved image of a copper wire, and we marked the 4 lines on each picture to be further analyzed. The histogram image of each right line marked in the previous output image is shown in these pictures, and a Gaussian fit was applied. We read the full width at half maximum of the image to determine the spatial resolution. And we conclude that for the polycapillary setups with 3.5 centimeters, the spatial resolution is 385 micrometers. Since when using the X-ray collimation optics, only a portion of the X-ray photons will pass through the X-ray optics and reach the detector. Therefore, the transmission efficiency is another important factor when considering the measurement time. So to extract the measured intensity, the peak count values are listed in the table below. It should be noticed that the background noise are subtracted from the average peak value. In this comparison, the polycapillary at 3.5 centimeter gives the highest photon intensity. So in this comparison, the polycapillary optics at 3.5 centimeter is the optimal choice because it provides the highest spatial resolution and the highest intensity gain. In the end, in order to verify the feasibility of the setup for light elements, aluminum foil was performed, and it is placed between the copper plate and a titanium plate as a sandwich structure. The X-ray beam is a broad beam, so we use a 100 micrometer pinhole to focus and collimate the X-ray beam to a smaller focus spot. Then we scanned a line on the sample and measured the spectra for each point. The titanium, copper, and aluminum peaks are extracted and then replotted in the middle figure. And the distribution of these 3 elements shows agreement with the sample structure. And in the end, a Gaussian fit is applied to the aluminum foil signal to obtain the spatial resolution of the imaging systems. A feasibility study of X-ray fluorescence used for continuous and direct heavy metal analysis of industrial processes and environmental emissions is provided. The study shows that the XRF technique provides the capability to perform in situ assessment of heavy metal contaminations in incineration plant. So if the metal composition of the ash was known on site, it will be possible to adjust the washing process to optimize the content in the fly ash. And since proper selecting the filter material and techniques is important for reducing the background noise and thus improving the detection limit. For chromium in solution, a limit of detection of 0.25 milligram per liter was reached, which is lower than the environmental limits at 2.5 milligram per liter in Sweden. By optimizing the XRF filter, it is sufficient to monitor the tens of concentrations for critical elements below the environmental limit. The full-field XRF imaging setup demonstrates the capability to obtain spatially and spectrally using a polycapillary optics, which leads to a significant reduction in measurement time when comparing with the scanning method. So the archaeology and exploration industry could benefit from the full-field XRF measurement. In the end, for light element detections, air absorption must be considered. Maybe a helium gas is suggested for the future works. A preliminary line scanning measurement demonstrated the XRF mapping on a microscope level. By measuring the sulfur and the sodium distribution in the impregnated wood chips, it might improve the impregnation techniques in the paper industry. And since the last work is still an ongoing work. And thank you very much.